In this video, I'm going to start by discussing the two different theories of light, that it can behave both as a wave and as a particle. I think the understanding that light is a wave and the electromagnetic spectrum should be something we're familiar with from GCSE physics. And then we're going to go on to use this to explain how we can use light as an analytical technique to identify elements, for example, that are existing in the corona of stars. So let's start right back at the beginning. The electromagnetic spectrum is something I hope that we're all familiar with. We can see we've got radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. As we move from one end of the electromagnetic spectrum to the other, what changes about light is both its wavelength and its frequency. So radio waves have a very long wavelength and a very low frequency. Gamma rays, on the other hand, have a very high frequency, many waves per second, but a very short wavelength. And visible light, which falls in the middle, you may be familiar, I hope, with the experiment from GCSE physics, where if you pass white light through a glass prism, refraction causes all the different colours to be split, because each colour of visible light has its own specific wavelength and frequency. We can see red light there with a wavelength around about 700 nanometers, as opposed to blue light, the other end of the spectrum, which has got a wavelength of around 400 nanometers, but a much higher frequency. The wavelength and frequency of light are related in this equation here, where c, the speed of light, equals wavelength times frequency. The speed of light is a constant, 3 times 10 to the 8 meters per second, which means that when we're using this equation, and you may well be asked to, we need to be sure that our wavelength is in meters, because the speed of light is in meters per second. Now, when we're talking about frequencies of visible light, often our questions tell us that the wavelength of this specific frequency of light is, for example, let's go with 420 nanometers. You're expected to know that a nanometer is 1 times 10 to the minus 9 meters. This one's actually quite easy to remember because n for nano, n for 9. So in terms of meters, that would be 420 times 10 to the minus 9 meters, or 4.20 times 10 to the minus 7 meters would be the more conventional way of representing that. So a simple example calculation: calculate the frequency of light that has a wavelength of 452 nanometers. Well, I know that speed of light equals wavelength times frequency. I know the speed of light. This is given to you usually in your data booklet at A-level, so that was 3.00 times 10 to the 8 meters per second. The wavelength here is 452 nanometers. I need to remember to change that to meters, so that would be 4.52 times 10 to the minus 7 meters. I can then rearrange my equation. So frequency is going to equal speed of light divided by the wavelength. So that's 3.00 times 10 to the 8 divided by 4.52 times 10 to the minus 7, and that comes out at 6.64 times 10 to the 14 hertz. It's useful at A-level to get a feel for the size of numbers. So wavelengths, very tiny. Frequencies, really quite large. 10 to the power of 14 is a big number. Now, it turns out that light, as indeed anything, can exist as both particles and in the form of waves. This is known as wave-particle duality. It's a concept that's central to quantum mechanics. And I'm not going to go any further here, but there are lots of great videos, TED Ed, and also on YouTube. And Einstein went one step further. He took this idea of that light being able to exist as particles described it, rather than being a solid particle, which didn't fit any of the experimental or theoretical data, that our particles of light should be more thought of as tiny packets of energy. And these tiny packets of energy he called photons. Max Planck went on to show that the energy of the photon is directly proportional to the frequency of the light. E equals hv. This is the second equation in this topic that you need to know. H stands for Planck's constant, 6.63 times 10 to the minus 34 joules per hertz, which means that the energy of photons is going to be per joule. Okay, so another quick calculation. Calculate the energy of a photon that has a frequency of 3.5 times 10 to the 13 hertz. Well, we know that energy is directly proportional to the frequency. Using Planck's constant, and this is always given to you, so check your data booklet if it's not in the question, 6.63 times 10 to the minus 34. And we just need to multiply these two numbers together, so it's going to be that times 3.5 times 10 to the 13. Multiply those two together, and we get 2.32 times 10 to the minus 20 joules. And this is the energy per single photon. And I'm making that clear because quite often questions are phrased in a way that ask you to calculate the energy for a mole, in which case you'd need to multiply up by Avogadro's number. And if they wanted the answer in kilojoules, then we would need to divide by 1,000. Okay, so let's go back to our familiar prism experiment. And this is what we've got here in this top line of this diagram. So if I shine white light through a prism or diffraction grating, then that white light is refracted, split up into all the colours that make up white light, from red through to blue. Okay, so we're all very happy with that. We're just talking about visible light here. However, if we, and I'm looking at the second experiment here, if we take that white light and shine it through a sample of an element, and then through the diffraction grating, we see a slightly different picture. We see our visible spectrum, but you can see quite clearly here, in my visible spectrum, I've got a series of black lines. This indicates black means no light. These specific frequencies of light are missing from the spectrum, which means that they've been absorbed by the atoms in the sample of gas that I shone the light through before I put it through my diffraction grating. If we go back to the Bohr model of the atom, we know that electrons exist in defined or quantized, new word here, energy levels, and these are specific to the atom concerned. So when we shine our light at our sample of atoms, the atoms absorb specific frequencies of light, and they use that to promote electrons from a lower energy level, for example n equals 1, to a higher energy level. Now the difference between these energy levels is also quantized. It's fixed and it's specific to an element. So the distance or the difference in energy levels, n equals 1, n equals 2 for hydrogen, delta E for hydrogen, will be different than it would be for sodium. And because we've got this direct relationship here between delta E and frequency, clearly the larger the energy difference, the higher the frequency of radiation that would be absorbed to promote an electron. So if I were promoting it, say, to the n equals 3 energy level, bigger delta E, bigger frequency of, or greater frequency of energy that would be absorbed. We can calculate the delta E, the energy change for a transition, for any line on the spectrum given its wavelength. So in this case, we've got a faint line on the absorption spectrum of sodium at 569 nanometers. Calculate the energy change in kilojoules per mole. So first of all, I've got the wavelength, but what I really need is the frequency. So I need my first equation. Speed of light equals the frequency times the wavelength. So I'm going to rearrange that. Frequency is going to be speed of light divided by wavelength. So that was 3.00 times 10 to the 8 meters per second. I'm going to convert my wavelength into meters per second. So that would be 5.69 times 10 to the minus 7 meters, because I require my units to be all the same. And that comes out at a frequency of 5.27 times 10 to the 14 hertz when you plug it into your calculator. Now that I know the frequency, I can calculate the energy, because delta E equals hV. So H is Planck's constant, 6.63 times 10 to the minus 34, multiplied by the frequency, we've just worked that out, 5.27 times 10 to the 14, and the energy, 3.496 times 10 to the minus 19 joules. Now that is the energy associated with one photon being absorbed. But I don't want the energy for one photon. I've been asked for a mole, and I want it in kilojoules, not joules. So to convert it into a mole, I just need to multiply by Avogadro's number. Again, this will be given to you in your data booklet. So to convert to 1 mole, it's going to be 6 point, sorry, not 6. What am I doing here? 3 point, going too fast here, 96 times 10 to the minus 19, multiplied by 6.02 times 10 to the 23, which is Avogadro's number. And I want it in kilojoules per mole, so I need to divide by 1,000. And when I do that, the answer comes out at 210 kilojoules per mole. So using both the equations here to go from a wavelength of a line to find the energy transition in kilojoules per mole. So this is an example of an absorption spectrum that is taken from looking at a star. So if we look at light coming from a star, the light passes through its corona, and all the elements that are present in the corona will absorb specific frequencies of light, and so we get a series of spectrum that are overlaid on top of each other. From that, we can figure out which elements are present. So we can see in this star, for example, we've got calcium and hydrogen and iron and magnesium. Each of them is absorbing at different frequencies. And we know that's going to be the case because if each of the energy levels in a sodium atom are quantized at a different value to each of the energy levels, say in an iron atom, then in each case delta E is going to vary. And so the specific frequency of light required to promote an electron, say from n equals 1 to n equals 2, in each case, just as an example, is going to be different because delta E is different. A spectrum for an element is made up of a sequence of lines, and that sequence is specific, it's unique to that element. So why have we got more than one line? Well, if we think about it, we've got a number of possible different electron transitions. So if that is n equals 1, n equals 2, we've got 3 energy levels in this particular atom. Then I could have electrons transitioning from n equals 1 to n equals 2, or n equals 1 to n equals 3, for example. In each case, you can see there that the delta E is different, and so the frequency of radiation absorbed, the frequency of visible light that's absorbed in order to promote the electrons from the lower level to the higher level is going to be different, and each one is going to absorb a different frequency of light. We're going to get a different black line on our coloured background in terms of our spectrum. You may have wondered why in each of these diagrams we see the electron shells being drawn closer and closer together. The reason is this is what the mathematical models predict, and also we find this to be true experimentally. So when we look at a spectrum for atomic absorption, then we see our black lines becoming closer and closer together because the corresponding difference in delta E is getting smaller. N equals 1 to N equals 2, N equals 1 to N equals 3 is bigger but not quite as big as it was, and so on. If you're asked to describe what an atomic absorption spectrum would look like, we can describe it simply as a coloured background with black lines, and that they're getting closer together as the frequency increases. Another common question is what would be the effect on the atom if a photon of light of enough energy is absorbed? Well, if we absorb energy, say, from the UV part of the spectrum, so a photon of light with very high energy, then that would give us enough energy not just to promote the electron, but actually to lose it from the atom altogether. Essentially, our atom becomes ionized. Atomic emission spectroscopy is exactly the opposite of atomic absorption spectroscopy to all intents and purposes. Our spectrum is black background with coloured lines, once again getting closer together at higher frequency. And you'll be familiar, I would think, with emission spectrum because this is what flame tests are all about. Back at GCSE, if you put some potassium nitrate into a flame, you get a nice lilac colour. Strontium gives us a red colour, sodium gives us a yellow colour. These elements are emitting, giving out, specific frequencies of coloured light. And hopefully we'll just be able to reverse the arguments to explain what's going on. So in this case, what we have is that our sample, the atoms in the sample are excited. They absorb energy, in this case from a flame, and it causes electrons to be promoted to higher energy levels. They then drop back to lower energy levels, and as they drop back, they emit a photon of visible light or visible radiation. And that photon has a specific frequency because, as we know, when we drop back from one quantized energy level to another, delta E is quantized. And hence we get these specific lines. So we need to be quite clear about the language we're using to describe what's going on with emission spectroscopy, because we're talking about electrons that are falling from a higher energy level to a lower energy level because they've previously been excited. They've previously jumped up levels because the atoms have absorbed energy. And we need to be quite clear here, the atom absorbs energy, electrons are promoted to higher energy levels. Often when you read student answers, that isn't clear at all. So our electrons are dropping back to a lower energy level. The difference between our quantized energy levels, delta E, is directly proportional to the frequency of the photon of light that is emitted. Once again, with an emission spectrum, I've got an example here for hydrogen. We have a whole sequence of lines, and this sequence of lines is specific to the hydrogen atom. It would be a different sequence of lines if this was the spectrum for sodium or potassium or magnesium, because our electrons are able, we've got a number of possible movements. We could drop an electron back from a higher level from n equals 2 to n equals 1, or n equals 3 to n equals 1, or n equals 4 to n equals 1. Equally, because these are electrons that are dropping back from a higher level to a lower level, it might be that they're dropping back to n equals 2. And in each case, I hope we can see quite clearly that the distance or the difference between these energy levels, difference is a much better word, don't use the word distance, the difference between these energy levels differs in each case. So as delta E equals hv, we can see that we're going to get a different photon of visible light emitted for different movements. So what might this look like in terms of a perfect answer? This is one area of chemistry where it's more than possible to write yourself a series of perfect answers and commit them to memory. You've got to be very, very clear on your language at all times. So we're saying here that atoms absorb energy and they promote electrons to higher energy levels. Our electrons are then falling back to lower energy levels. When they do that, they emit a photon of visible light, and it's got a specific frequency. We need to mention that each of these energy levels are quantized, and that essentially because delta E equals hv, and always put the equation into your answer, there are a number of different transitions possible, each with its own specific delta E, and hence a different frequency photon of light is emitted, and that is why we get a series of lines. You'll notice that if we compare the absorption and emission spectrum for the same element, then our lines turn out to be in exactly the same places, i.e. the frequency of each of these lines is the same. And that's to be expected because since delta E equals hv, and these energy levels are quantized, whether we are looking at absorption and electron are being promoted, or emission, and an electron is falling back to a lower level, the difference between the energy levels, delta E, remains the same. Therefore, the frequency of visible light that's either absorbed or emitted is going to be the same, and hence the lines on the spectrum are in the same place. And finally, we come to the end, but the last thing to be aware of is that for a hydrogen atom, the sequences of lines have been given names. So where we have electrons falling back from higher levels to n equals 1 is known as the Lyman series. So in each case, we've got different delta E's, different frequencies of photons being emitted, so we're going to have a series of lines. If our electrons are falling back to the n equals 2 level, it's the Balmer series, and n equals 3 is the Paschen series. If this has been useful, hit the subscribe button, the effortless way to support your studies, and by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.